In this lesson, we're going to be talking about logarithms. So logarithms are a new concept that allow you to solve for an unknown variable that's in the exponent of a function. So as you know, when we're solving for something like 5x equals 30, we can use opposite operations. So we can divide both sides by 5 to determine that x equals 6. Also, when we're solving exponential functions, if you have something like 2 to the power of x equals 8, sometimes this will be a perfect cube or a perfect square, and you're able to solve for it simply by looking at what you have. But what happens if you have 2 to the power of x equals 10, where this is not a perfect cube or a perfect square, and there's no whole number value here that allows us to solve for what this unknown is in the exponent. And that is where logarithms come in handy. So in this lesson, we're going to go through sort of what a logarithm is, and then as we go, I'm going to show you how you can use logarithms to solve equations. So if we have in exponential notation, b, or some base to the power of y, is equal to x. In logarithmic notation, this is y equals log base b of x. So you can see here, the base of the exponent becomes what's called the base of the logarithm. The exponent goes to the other side, and the x becomes the body of the log. So how we say this is we say log base 3 of 9 is equal to 2. And that's because 3 to the power of 2 equals 9. So writing it in logarithmic form allows us to have it in terms of logarithms, and if this this exponent value was not a whole number, we would be able to use this to solve. So the next few questions are just some practice in changing between forms. You can think of exponential form and logarithmic form as sort of like changing from a fraction to a percent or a percent to a decimal. We're just changing forms. So these two things are equivalent to one another. They're just written in a different way. So for example, log base 3 of 27 is equal to 3, and in exponential notation, that would be 3 to the power of 3. So the base of the log becomes the base of the exponent. Our constant here, the 3, becomes the exponent, and that's equal to 27. Or here, log base 10 of 100 is equal to 2, would be the same as 10 to the power of 2 equals 100 in exponential form. And so here, in general, log base p of q equals n means p to the power of n is equal to q. And we can do the opposite. We can go from exponential form into logarithmic form. So here, the log base 4, because the base of the power becomes the base of the log, of y would be equal to x. It doesn't matter if you wrote this the other way too. Those are the same thing. On this side, we have, introduced an x there, shouldn't be there. So here we have log base 2 of 16 is equal to x, which you might have noticed is I had a 4 written in there. That's what this would actually be equal to. But in logarithmic notation, it's just log base 2 of 16 is equal to x, and over here, log base a of n is equal to m. So down here, we can solve for the missing variable. So here, log base 2 of 16 equals y. We can change that to exponential form. 2 to the power of y equals 16. So we know that y would be equal to 4. Here, y equals log base 9 of 3 means 9 to the power of y equals 3, which would mean that y is 1/2. Just a little side note, something to remember, is that if you have 9 to the power of 1/2, that's equivalent to the square root of 9. So remember, fractional exponents, the denominator is the index of the root, and the 1 is a power inside the root. So this is the square root of 9. So 9 to the power of 1/2 is equal to 3. Over here, the base is 9. So 9 to the power of 1/2 is equal to x. So again, this means the square root of 9, which is 3. Now down here, you'll see we have 1 equals log x. And it would appear that we're missing the base of the log. When a base is not written, this is called a common logarithm, and it means the base is 10. So log of x essentially means log base 10 of x. So here, this means 10 to the power of 1 equals x, which means that x equals 2. And for question E, we have log base 2 of -4 equals y. When we change this into exponential form, 2 to the power of y equals -4, and we know that this has no solution. We can't raise a positive number to any power and get a negative solution. So a little note that we'll use going forward is that the body of the log here cannot be negative. Now, going back to the idea of a common logarithm, a log function with a base of 10 is called a common log function. We saw one example on the previous page. When it's written without a base, it's assumed that it is base 10. Now you may have noticed on your calculator that there is a log button. So on most calculators there is a log button. Mine is right here under the second function button. That is for a common logarithm. So if you have log base 10 of 2, you would be able to put that into your calculator, and you would just put in log 2, and it equals 0.30103. That means 10 to the power of 0.30103 is equal to approximately 2. Same for log of 5. You could type that into your calculator. 0.69827, that means 10 to the power of 0.69897 is equal to approximately 5. Remember, these decimals are rounded, so this is just approximate. We can only use that log button on the calculator if it's a base 10. So, a few ideas to remember. Here, if we have log base a of a, it will always be equal to 1. And the reason for that, I'll show you an example with an actual number, is that if you have log, let's say base 4 of 4, when we write that in exponential form, let's say this equals x, that means 4 to the power of x equals 4. Well, that will always be 1, because if the base here is the same as this body of the log, then this exponent will always be 1. So when you have log base a of a, or a number and itself, it will always be equal to 1. Similarly, log base a of 1 will always be equal to 0. So the reason for that is that, let's say for example, we had 5 and 1. Well, this would be 5 to the power of x equals 1. And we know that this would have to be 0. So x would have to be 0. So when you have log base a of 1, it will always be equal to 0. Here, log base a of a to the x will always just be equal to x. So an example of that would be log base 5 of 5 to the x equals x. I should use a different variable, but basically what this means is that this is just going to be equal. So that means that log base a of a to the x would just be equal to the exponent over here. And here, if you have a to the power of log base ax equals x, What that means is that, and I'll write that down, so let's say you had 6 to the power of log base 6x. When you write that in exponential form, let's call it y. Here, if I wrote this in, sorry, not exponential form, in logarithmic form, this would be log base 6 of y equals log base 6 of x, because the exponent goes down to the other side. So that means essentially that y and x would be equal. It means that these are the same. These two you won't see that often, but these two you will see all the time. One more note is that when we're working with logarithms, we work with something called natural logarithms. So they come in handy when we're working with a number called e, which is Euler's number, and it's equivalent to 2.718, and it's irrational, so approximately 2.718. It's just like pi in that sense, in that it continues on forever. So e is not a variable, it's a constant. Now, the thing about e and why it's important, here this is just what e is equal to. So as you plug in different values of n, you'll see that this approaches 2.7181. We could spend a whole bunch of time learning about e. For our purposes, the thing to know about e is that when you have log base e of x, it's equal to what's called a natural logarithm. So this is a natural log. It's ln of x. Basically, the inverse of an exponential function is the log. So for example, y equals e to the power of x is inverse of y equals log base e to the x. So these are inverses of one another. We're going to spend more time talking about inverses because we're also going to be spending some time graphing these logarithmic functions. So that wraps up our first lesson on logs. And like I said, we're going to spend a lot more time working on these.